All right. Well, welcome everyone. Thank you for joining us for today's webinar, Incident Investigations, presented by Robert Magraw and Roger Stokes. Rob Magraw is a Quality and Operations Manager and Process Safety Senior Principal Consultant, and Roger Stokes is a Process Safety Principal Engineer who work out of our UK office. Today, Rob and Roger will provide an introduction to incident investigation, emphasizing the importance of determining what happened before delving into why, and then further into root causes. The theory will be demonstrated through a presentation of a case study. Now, I want to go over a few housekeeping items. Please type any questions that you have into the Q&A box in the Zoom control panel, and our tech staff will respond to the questions. And finally, at the close of our webinar, we ask that you provide feedback by responding to the survey that pops up as soon as you close your window. We're excited to have Roger, Rob, and Amber present today. So without further ado, I'm going to turn the time over to our presenters, Roger and Rob.
Okay, good morning, everyone. Good afternoon, good evening, depending where you are. So this webinar is number 7 in the series we've been giving, and the topic, as Naomi said, is incident investigation. What we've got for you today is an introduction into why we need to conduct investigations, which I will take, and then I'll hand over to my colleague Roger Stokes, and Roger will walk through the critical steps in the sort of scientific approach to investigation process and demonstrate those through a case study. Okay. Firstly, a quick introduction to BakerRisk for those of you who may not know us yet. BakerRisk is a US-based company headed in San Antonio, Texas, with offices throughout the US and Canada in Houston, Chicago, Los Angeles, and Toronto. We also have 2 test sites in Texas where we do full-scale vapor cloud explosions, amongst other fun things. Roger and I will be talking to you today from the BakerRisk Europe office in Chester in the UK. In terms of Egypt, BakerRisk has a long history of work in Egypt, including us taking an active role in peer reviewing the recently developed Egyptian PSM standards and guidelines. We perform lots of studies, variety of studies across industries within Egypt, and maintain a presence through our partnerships with multiple trusted partners within Egypt. Okay, so incident investigation. So the first question is why do we investigate? Why do we need to bother investigating? So we want to demonstrate this by looking at some examples of where things have gone wrong. Often events that get cited, the likes of Flicksborough, Buntsfield, Piper Alpha, Texas City, etc. But what I want to show here is some sort of more recent events that demonstrate that industries are still having these major accidents on a regular basis. The first couple of these examples, BakerRisk personnel were actually boots on the ground investigating what went wrong. So clearly you'll see from these accidents that investigations are still in demand. But the question is, if we're investigating these incidents and they're still occurring, what is it we're missing? What are we not learning from these investigations? And we'll hopefully bring that up as we go through. So the first event here, this happened at the Husky refinery in Wisconsin, USA, on April 26, 2018. Now, this event clearly demonstrates how real events in the real world can escalate in unexpected ways that are often far more complex than the simplistic scenarios that we might evaluate for a QRA or even use as the basis for our emergency planning arrangements. So here at Husky, there was an explosion in the fluid catalytic cracker regenerator, and that caused flying debris, bits of equipment flying across the site. And one of these pieces of equipment punctured the asphalt tank that you can see in the picture here. The asphalt stored in the tank came leaking out as a fountain that you see in there. and that actually overshot the containment bund, the earthen containment bund, and flowed back into the process area, where it subsequently found an ignition source and caused significant further damage. So this is a video of the aftermath. Luckily, in this case, there were no fatalities. However, there were 11 OSHA recordable injuries and all the downtime of approximately 2 years. The resulting payout from the insurers at the end of 2018 was approaching $500 million. And that covered plant damage, business interruption, and cleanup costs. The next example we'll look at is Philadelphia Energy Solutions Refinery in Pennsylvania, USA. This was the 21st of June, 2019. And this is another event that escalated. An initial fire resulted in a major explosion. And in this screenshot, just taken during that major explosion, you can see a section of process vessel being ejected. That piece of vessel actually landed on the other side of the adjacent river. So there goes the explosion and the vessel flying out. So the consequences of this event, again, luckily no fatalities, surprisingly, 5 injuries, around $1.25 billion in insured losses, including around $1 billion in plant damage and $250 million in business interruption. As a result of this event, PES, Philadelphia Energy Solutions, went bankrupt. The refinery was closed, and if you look at the site on Google Earth now, you'll see it's completely demolished, and it's just a flat area. So the impact of these events on the business can be massive, as well as the immediate safety impacts. Slightly different event. So this demonstrates these events don't just happen at production and manufacturing facilities, but actually can occur anywhere that high hazard materials are present. Some of you may recognize this. This is the port of Aqaba in Jordan. The event happened June the 27th, 2022. An ISO container, you can see here, is being lowered, containing 25 tons of chlorine. It's being lowered onto the ship. The lifting system failed and it dropped, resulting in 13 fatalities and more than 256 injuries. And what's incredible about this is the speed with which that toxic cloud spreads. Here you can see the ISO container that fell and the punctures from landing on the support structure on the vessel punctured the hole in the ISO tank. An even more recent example, this includes a major explosion at a chemical plant operated by Shandong Yudo Chemicals in China, May 27th of this year. The details are pretty scant, but it's believed to be between 5 and 11 fatalities, 19 injured, and you can see from the picture major damage to the facility itself and also lots of adjoining facilities as well. Back to the USA. So this is Smitty's lubrication plant in Roseland, Louisiana, August 22nd, 2025. And you can see there's a pretty well-developed fire in a tank farm. Took 2 days to extinguish. Just look at that video and look how closely spaced those tanks are and how close the bunding is to the tank. Much cleanup work to do after this event. Okay, so there's a history of major accidents and a continuation of those accidents. So why do we investigate? Okay, here's a list of some of the reasons. It's not an exhaustive list. There are also lots of other things. So first of all, we want to understand what happened. Once we understand what happened, we can look at why it happened. When we understand why it happened, we can identify the root causes behind those immediate causes. And then once we've done that, we can take action to prevent it reoccurring. This is the most important thing. And you can do root cause analysis to the end of time, but if you don't do anything with the results, nothing is going to change. So that's the critical point. So we can take that learning and we can share it amongst our own organizations. We can share it outside our facility to others in industry. And that learning helps develop the safety culture within the organization to reduce the likelihood of similar events happening in the future. Okay, and the second to last point there, to satisfy stakeholder needs, we will cover in more detail as we go forward. But as I say, there's lots of others in terms of legal, insurance, all those lots of other reasons why you might want to investigate an incident. So looking at the legal side of things, looking at the European Union first, where we've got high hazard regulation under a directive commonly known as Seveso. We're currently in version Seveso 3. And this directive from the EU must be implemented by all EU member states. So I've underlined certain statements in that clause there that emphasize the need for understanding what happened by means of an investigation. So understanding the circumstances, prevent reoccurrence, and the other important there, update if further investigation reveals facts. So that's an acknowledgement that on day one, you will not know all the facts. You need to do some investigation. You need to do some digging into the information to understand what's gone on, and then that may likely change your view as you develop the ideas. So that's European Union. In the US, we've got the OSHA standard 1910-119. So this is process safety management. And again, there's a whole section in there on incident investigation. I've just pulled out one clause that says employers shall investigate each incident. And the important thing on this one is that they've said it's not just incidents which have resulted in, but also could reasonably have. So this is putting a duty on the operator to investigate those events that could have resulted in a major accident. Within Egypt, we've got the guidelines from the Ministry of Petroleum and Mineral Resources, incident notification, investigation, and reporting. And again, we're saying that operating companies shall openly investigate all incidents, and this preventing recurrence, continuous improvement. So all that same theme runs through all these guidelines. If we look at what industry groups are saying, this is the risk-based process safety temple diagram from the CCPS. And again, you can see on that one of the key things for learning from experience is incident investigation. Other industry organizations, such as the Energy Institute, have a similar management framework that has, in the EI framework, its element 19 is incident reporting and investigation. So all the legislation and industry good practice are telling us all, if something goes wrong, investigate it, find out what happened, and learn from that investigation. I said we would go back to stakeholders because they are many and varied. This slide just lists some of the key players that might have an interest in the outcome of an investigation, although they may have different objectives and opinions on what's involved. So clearly, the operating company, the ones who've suffered the incident. So there might be a site level investigation, a corporate investigation. The owners of that business may be interested. There'll be other affected parties. Could be employees who've suffered injuries. Similarly, contractors, third parties, any parties who may have been directly or indirectly involved in the event. You've then got authorities, so those with some sort of regulatory or oversight kind of role, local authorities in the district where this happened, your regulatory authorities, and the emergency response organizations that may have responded to the event. Clearly, at some point, insurers will probably be asked to contribute towards the loss. So the insurers are going to be interested in what happened and why it happened. And then others, many sort of lawyers representing various stakeholders. If you've had a piece of equipment that is part of a license process, then the organization that licenses that is going to be interested in what happened and why it happened, and many other things such as trade associations who may want to share information with others about that type of equipment or how to operate it or not operate it. So some examples of how the objectives may vary, and sometimes this can seem incompatible or even in conflict. So we need to be careful how we avoid and manage these multiple conflicts. So here, for example, injured party, maybe they're just purely interested in can they get compensation. Insurers need to understand how much they need to pay out, and obviously they'll be trying to minimize that. Lawyers may be looking to get, we want sufficient information to apportion blame, and that's as far as they want to go. Regulators looking to see if any laws are broken, but the most important, I would say, there is the owner, because they're the ones who really need to understand what happened, to learn from it and make sure it doesn't happen again. So managing different interests, this is a challenge, and there is one accident site with all these different parties vying for position and gaining information. So we need to ensure there's some degree of cooperation, although the goals may be different. The actual interests in terms of getting a true picture of what happened, why it happened, is important to all. So one of the key things here we find is to develop a protocol. So this is a protocol that may help complex tasks such as testing functionality of a piece of equipment, dismantling evidence, or removing evidence from the site to somewhere else. So developing a protocol between interested parties can help clear blockages in those investigation processes. Excuse me. Okay, so that is a very brief run through why we still continue to need to investigate accidents, who stakeholders might be, and what some of the pitfalls are. I'll now hand over to Roger, who will walk through the actual process and an example.
So good morning, good afternoon, everyone. I'm Roger Stokes, chemical engineer with BakerRisk, and I'm pleased to go through an example with you, and hopefully you'll find it useful and interesting. So this is an abridged version of the investigation process, just going through some of the key points. Start off with a flow chart. You have an incident, could be an accident, it could be a near miss, as Rob explained. Key steps initially are looking at safety and environmental issues, so it's securing the area, but also we need to look at managing the scene, controlling access, preserving evidence, and perhaps a chain of custody of items of evidence. A team needs to be activated. The team might depend on the severity of the incident, and the appropriate participants are assigned. If it's a big incident, you might get people from outside the site, and you need to define scope and responsibilities. We then collect and analyze the evidence, which could be physical evidence, it could be interviews with people, and then we look to determine cause, which could be initially the immediate cause, what's contributing to that cause, and then further drill down into the root cause, which is typically a failure of a management system. We develop recommendations, some which we may need to put in place before we start up, and some perhaps we can start up, but we need to put these in the longer term. A report's then issued. There might be a legal review process. Items are set, and who's going to do what and when. There's a quality control mechanism to make sure that that report is good and systems are audited. And of course, as Rob said, we need to then to learn this. It's sharing the cause with other people and then embedding the learning into our procedures and management systems. So evidence collection and cause determination. There's various evidence that comes in. It might be a witness, what people saw, what they smelt, what they heard, what they were doing, and what others were doing. They might have evidence on their personal electronic device, on the phone. There might be some video data from the site security system, which might have some timestamps and so on. There's then physical evidence, so where the bits are, what they look like. We might need to do some physical analysis. There also may be paper records, but increasingly these days, obviously, we've got electronic data to secure and to examine. And all of this information is used to analysis process and look at hypotheses. So what happened, how it happened, and that's also involves developing a timeline, which could go back sometime prior to the incident itself, depending on the connections between the history and the incident. And this is a cyclical process. You might find you need more information, go back and collect more information. But you can analyze the data and establish immediate causes, may get requirement for new information, but then we're determining the root cause, and ensuring that we include human factors in this issue. So what sort of evidence have we got? We got to first of all secure the time sensitive information. So here's a list of what may be time sensitive. It could be witness statements. They forget what they saw. People talk to each other and maybe change their thoughts change onto what happened. Samples of fluid, data from the computer. Sometimes you lose it very quickly, which can be a problem. The photography on the site and video, same issue. Handwritten logs, work permits, surveillance video, etc. So all these things could be time sensitive. You might have other stuff that's not as time sensitive, so that there might be photographs and video that can be preserved, data on the computer, but beware. It's amazing how many investigations I find where the data's written over in weeks or a month. Bits and pieces, preserve them, make sure we can take them and analyze them without them suffering from other deterioration. Records from labs and all the engineering data that we're all familiar with. The scientific method for investigations based on NFPA 921, which starts off by saying, what's the need? What's the problem here? Let's define it. And then let's collect data. So we then analyze the data that we've collected, and then we develop a hypothesis called inductive reasoning. What could have happened? What may have led to this from occurring? And there might be several hypotheses to start with, and then we need to test them. What do we need to demonstrate that this hypothesis could have occurred, or indeed might not have occurred? And let's test these, and we might come down to only one possible hypothesis. It might be two or three. That's not always the case. But there's feedback loops there as we develop and test hypotheses. We might again get more data which we look at and so forth. So that's the scientific method. And of course, at the end, we then select the final hypothesis. This is another slide, the British Standard. It's a similar approach, using scientific tools to identify the cause and using data to test that. There's various terms for cause. I won't read through all of these in detail, but there's an immediate cause, and I think the third definition there is probably pretty good. The final act in a series of provocations that leads to a particular result. So the last thing that happened before it went bang, the pipe burst, the valve opened, whatever it is. Then we have the underlying cause or causal factors, which could be defined as unsafe acts or unsafe conditions. It's something that contributed to the incident but wasn't the final event. So it could be system or organizational procedures, tests not carried out, etc. Then we get into root cause, and this is really about management systems. If you haven't got down as far as management systems, you're not at the root cause in general. So it's the second definition here, a fundamental underlying system-related reason why it occurred and identifies a correctable failure in the management system. But the other definitions are similar. So the root cause, the concept of root cause, it's a management system we're looking at, and there are usually multiple root causes. Remember, an event is not a root cause. Failure to follow procedure, for example, is not a root cause. Why didn't he follow the procedure? What are the systems behind that? And of course, the risk stays there until we've implemented the remedies. So various methods to get to root cause. There's the 5 whys. You keep asking why until you run out of whys. There's a fishbone diagram, which gives you cause and effect. There's various forms of structured root cause analyses. It could be a logic tree or perhaps a predefined tree. One example is Taproot. BakerRisk has got a system called Cat Tree, and there are many others. Increasingly these days, we consider barrier analysis. What are the barriers? Which ones should have stood up? Which ones failed? And there's methods like Bowtie and EI's Energy Institute's Tripod Beta to look at that. Or you can use a combination. There's no firm rules on which system you use. You might have a combination, so you might have a predefined tree and then start asking whys beyond that. So this is the case study. It's made up for this presentation. It involved an explosion and fire at a chemical plant, and we start with the timeline. So here we have a pump that tripped, followed by a high pressure alarm. The pressure goes up and reaches the relief valve pressure, and 5 minutes after that, there's a sudden sound of gas escaping, and 2 minutes after that, there's a huge and devastating explosion. And this is what it might look like. Big bang, lots of destruction of property and plant, and of course injuries and fatalities. Here's an example of some physical evidence. This is a pipe that's failed. We don't know why it's failed yet. We needed a lot of work to establish that. But if it was a pipe failure, pipe rupture, let's look at a simple fault tree for analyzing that. We know we've got the pipe ruptured. We also know that the pressure went higher than normal, and that was because the pump tripped. But normally that shouldn't lead to a pipe rupture. There must be something else going on here. So we start putting together our hypotheses. What might have caused this to happen? And this is one way of doing it, putting together a hypothesis matrix. So the scenario we're looking at, maybe the pressure went too high. It exceeded the burst pressure of the pipe. And to verify that, you'd look at the records from the computer. You may do a metallurgical inspection of the pipe. And then you hypothesize, you look at your findings and you decide whether that's valid or not. there might have been a loss of internal wall thickness. You do a metallurgical inspection to validate that. It could have been external corrosion. Again, do some metallurgy. Somebody might have put the wrong pipe materials in. That happens all too often. Could have been hit by a passing vehicle. Let's look at the evidence of the pipe. Let's look at where vehicles were. There might be some security camera. Something fallen on it and caused it to rupture. Somebody accidentally cut into it. Let's look at the work permits and maintenance system. And then we look at all of this, so we'd analyze it. So in this example, let's look at the rupture due to excess pressure. If we go to the findings column here, we find that the relief valve pressure has not been exceeded before the pipe ruptured. So it was within its design pressure. There's no evidence of high pressure being the immediate cause. What about internal loss of wall thickness? We looked at the pipe. Yes, we had a loss of wall thickness due to corrosion. So that's one valid hypothesis. What about external corrosion? No, there wasn't any. What about the materials of the pipe? Yep, they were correct. So it's not that. Was it hit? No, there was no sign of it being hit. Anything drop on it? No. So in this case, we've gone through and found one hypothesis which is valid. We've lost wall thickness on the inside of the pipe due to corrosion. Oh, sorry, last one. Nobody accidentally cut into the line. So we have internal corrosion. We start asking, well, why have we got internal corrosion? Well, it could be solids entrainment in the gas stream. That could be one hypothesis. It might be high moisture. It might be high temperature. It could be liquids accumulating at a low point. Maybe the thickness checks weren't accurate enough. So we look at all these hypotheses. We collect data, we go through, discuss it perhaps with subject matter experts. And we find actually here we have a situation where it was indeed high moisture that increased the corrosion rate. So if we go back to our fault tree that we had earlier, we now know that the pipe corroded below minimum thickness, and this was as a result of high moisture. And so the recommendations you might make from that investigation so far would be to find out why we had high moisture, and look at and make sure and then reduce the levels of moisture to those specified by the original design. We might then conduct more extensive thickness checks in other areas to see if there's any other possible failure location. And once we've done that, and maybe we can restart. We've repaired the pipe. We've checked everywhere else. We've reduced the moisture levels to the original design. But what about the root cause? We haven't got to that root cause at this stage, and there is another leg on the fault tree. So we start asking, why is the moisture level high? Well, moisture level is high because the process conditions were changed slightly, and we didn't consider the impact of the change in moisture levels on the piping. We then find that the management of change system wasn't used. And this change was made by a new engineer who didn't know about MOCs, and that for when an operating temperature was changed just very slightly. And then we find that he's not been trained on the MOC procedure. Why wasn't he trained on the MO procedure? Well, it wasn't sufficient. The training procedure for new graduates didn't include the MOC training course. And then at more of a management level, they hadn't audited the training procedure for 10 years. And that was because the management audit process didn't include the need to review the training procedure. So we're really getting to the bottom of this now. So one of the methodologies I mentioned earlier is taproot. So we'd go through a structured tree, and we'd look through the various potential causes. And in this case, there's training involved where we missed the required training, and the instruction for MOC training needs improvement. The NI needs improvement. We also found on the management system that the standards, policies, or admin controls were not used. So we had a policy for MOC, but it wasn't enforced. And then the other circle here is around the audits and evaluations were inadequate. It lacked depth. So we go back to our fault tree. Okay, high moistures increased the corrosion. We know operating conditions were altered, and we didn't use the MOC system. And there's reasons behind that we've just discussed. But we also found that the condition monitoring hadn't identified the increase in corrosion. And then there's a whole new leg on the fault tree where we start looking into asset integrity. So back to our hypotheses. What are the potential reasons or causes of failing to detect the increased corrosion? One could be maybe the corrosion rate's gone up rapidly since the last measurement. We know the moisture levels have gone up, but, so that's one possible cause. The other one is other possible scenarios that historic measurements weren't conducted correctly. So let's review the system for measuring wall thickness. Maybe the data analysis of that historic measurement, those historic measurements was incorrect. So let's try and replicate the analysis and compare it with the site figures. So we carried out the analysis, and what we found was that the corrosion rate hadn't increased significantly since the last measurement, so that hypothesis was false. We looked at whether they were conducted correctly, and we found that they were good. They did the correct used the correct method and produced the correct results for thickness. But then we found, unfortunately, that the analysis of those historic trends was incorrect, and we replicated it, and we found that excuse me, the analysis that they had did not use the highest rate of metal loss. Here's the thickness history. So the columns, these are the dates. So in 2000, we measured 3 different points, about 15 mil thick. 2010, arguably a bit of a big gap, but not much loss, with some loss of thickness. 2013, lost a fair bit more. And of course, you can calculate the rate of thickness loss on a short-term or a long-term rate. So the short-term rate of thickness loss, 1.3, long-term rate was 0.37. They used the long-term rate, and the retirement dates calculated down to a minimum 6.2 millimeters, well beyond where we were. So we had plenty at the time. We had plenty of operating life left. So this just tries to depict it. Here we've got the wall thickness up this side. The retirement thickness is along this line here, and these are the years of operation. So it started off a little bit loss of thickness, then it was pretty stable for a number of years, then increased. So the system effectively looked at the very first data point and the most recent one to calculate a retirement year in year 22. But of course, what they should have done is look at the highest rate of corrosion using in this case, using the last 2 data points, which have actually predicted a much quicker rate of metal loss. And in fact, it was almost consistent with the year of rupture. So we have a number of recommendations for the second immediate cause. We've got software settings were wrong on the computer program that calculates retirement dates. But we find that the maintenance personnel needed to be trained. The trend data wasn't visible, it wasn't visual, it was just numbers. So a plot of it would be pretty helpful, like I've just done. But we also have on the second root cause, why didn't we detect this? Well, the maintenance planner didn't understand the software properly. He was new and hadn't gone full training, the company had recently merged, and the planner was moved from a different organization. The management of organizational change wasn't carried out effectively after the merger. And we then found that, well, that was because they didn't actually have one. They didn't have a procedure for management of organizational change. So recommendations for the first cause, which was the straight management of change, changing the operating conditions, was to update training manuals, make sure graduates go through the full training, make sure MOC is there on refresher training as well, and have a better management audit system to make sure we audit the MOC and the training process, and make sure the training records of staff are good enough, and we can see the competencies they have and what they need. So for the second root cause, the organizational change issue, well, let's include that in the MOC procedure, and update the training manual and train the staff appropriately. And of course, the sort of generic root cause is connected with management of change. So from this incident, the lessons learned were about management of change, and many of the incidents are, in fact. So make sure people know about the MSC system and management of operational change. Make sure the training procedures are good enough around the company. Training and performance assurance. So what are the local training plans? How do we assess the competencies? Are they reflected in what the staff know and understand? And are there any other essential training requirements that we've missed and need to be conducted? And then, of course, auditing. Need to improve our management auditing process to make sure we look at these the training and the competency requirements. So just a slide here on generally on investigation pitfalls and tips. There are many methodologies around. Don't be forced down one because somebody says use that. Try and pick an appropriate method for the incident that you're dealing with, and don't start root cause investigation until you know what has happened, as Rob said at the start. A lot of it's good old-fashioned police work, asking questions, talking to people, finding out what happened, not assuming anything. And of course, these days we've got a lot of modern technology we can use, but we've got to be aware of it as well. And we mustn't forget human factors. So this is performance influencing factors that can affect the barriers that prevent these incidents from occurring. Don't jump to conclusions. Using the scientific approach makes you think outside the box and look at other possible causes, because we want to try and remove bias as best we can. Oh, this happened last week. I know exactly what happened this week. Oh, this happened last year. Oh, you shouldn't have done that. That was a silly thing to do. All these things need to be considered. And you might want to also consider the independence and competence of the investigator. So BakerRisk conducts incident investigations. Sometimes there might be, if it's a big incident or there's potential wide learning, it might be better to do it externally rather than internally. So external investigators may have a role. It could be somebody from another plant, or another site as well. But where there's management system issues, you need sometimes an external view to appreciate the problems. So that's the end of my talk. And Rob, so thank you very much for listening. It's time for questions.
And before we do that, we're going to invite Amber to hop on and give us a recap of what's been discussed. So, Amber?
Yeah. Hi everyone. Thanks Rob and Roger. I will not add that much. You almost covered everything, but I want to share with attendees that there is some level of incident which is really could cause a significant consequence. Really need to be investigated by independent consultant or not only independent consultant and competent, because I have seen myself that really big incident, and some companies they still believe that they can investigate inside internally. So humans are biased, not necessarily to intentionally biased. Sometimes not intentionally, but they bias to their company, they bias to their people. So it's better to really know what exactly happened to avoid reoccurrence for those uh, hypo incident could lead to significant consequence. It's better to have independent consultant and competent consultant, because the management of the operator need to know exactly what happened to avoid reoccurrence. And without cold eye, somebody from outside, and he know what he's doing, probably will not know exactly what happened. So this is my message. I strongly recommend this, and that's it, Naomi. Thank you very much.
Yes, thank you for your recap there, Hammer. I'm going to go ahead and ask some of the questions that did come up during the presentation, just as a reminder to our attendees. If you haven't already done so, be sure and type those questions into the Q&A box in your control panel. So one of the questions is, when should an investigation start?
I'll take that one, Roger, if that's okay.
Okay, yeah.
As soon as possible after the event. Obviously, if it's a major event with significant damage and possibly injured parties, then obviously that has to be dealt with first, and the situation made as safe as possible. But getting in and starting to gather evidence as soon as practicable after the event is critical. As Roger mentioned, there's this time-sensitive data. Capturing that, if you've got the shot Roger showed of the failed piping equipment, as soon as that failed piping is exposed to the environment, the conditions are going to change, and you may not be able to discover using sort of metallurgical analysis how it failed if it's been allowed to degrade. So there's all sorts of reasons why you need to get in there and keep that scene as much as it was. Don't have people going in there changing the position of equipment or manipulating valves or whatever in an uncontrolled way, so you can retain the information on what the situation was in the accident condition.
Excellent. All right. Another question is, who should conduct the investigation? Can y'all speak on that?
Yeah, well, I think, as we said, it really depends on the scale of the incident, the potential for learning, whether it was a high potential near miss. All of these things had to be taken into account. If somebody fell over a doormat and hurt themselves, that might be appropriate to have it locally. If there was a large loss of containment that affected people outside the site, it might be considered that we need to get somebody in external to do this, which it could be somebody external from the site in a senior position in the safety department, or indeed, as Amir said, somebody externally who's got no particular prejudice, bias, whatever, to conduct an independent study. That's it.
Nice, agreed. Appreciate that. Why investigate if we already know what's happened?
Well, Roger, I'll let you take that one.
Okay. Yeah, that's fine. So yeah, often we think we know what happened right at the start. somebody pushed the wrong button. What a silly thing to do. But we'll make sure he doesn't press that button again. But of course, next week somebody else might press the button, and then we get the same incident yet again. So yes, we might understand what happened, but if we're not going to learn from it if we just tell the operator off for pushing the wrong button. Let's find out why he pushed it. Look at the procedures. Look at the data that's available to him. Look at the training, etc., and then we'll get to the real reasons for why the incident happened.
Gotcha. And I guess, this next question kind of follows that one. So do you stop once you know who is at fault?
Rob?
Well, as we said, the primary focus should be to identify the learning and get that learning back in the system to avoid it happening again. You're not looking for someone to blame, unless there is due cause. But people usually make mistakes because of a failure in the system behind it. They've not been trained. That training wasn't adequate. They've not got the appropriate experience. They're not familiar with the equipment that's involved. There's a whole host of reasons. So you really need to dig down to identify what those system failures are that caused those actions to happen, and then you can remedy those. So just working down, say, yeah, that it was that guy that pressed the button. So we'll cease his employment and everything will be fine. Is just totally the wrong attitude to an approach to take.
Agreed. Well, it looks like we've only covered a few of the questions that were asked. And to our attendees, if you have additional questions, please type those into the Q&A box. I want to ask one last question before we conclude the webinar. It's a little broad, but if either of you or both of you can speak on to why we keep having incidents.
Well, yes. I'll start off. We do, as Rob said, we do keep having incidents, and if you look at many of the large incidents and you start analysing what caused them, they're all very similar. And when you get down to a management level, we haven't looked at management of change properly. We haven't provided decent procedures or training, etc. We are not learning from these mistakes. We're not, perhaps that's because we're not sharing it widely enough, or maybe people aren't interested in it. I think one of the remarkable things about having an incident or a near miss, turning it into a positive, is it's a wonderful way of involving people in the investigation process, which educates the individuals as well as informs them about the processes and procedures. And I think this is a hidden benefit of doing the investigation. You can bring up the workforce. They appreciate that it is important and they learn from it. But we then need to embed it in the operating systems, into the operating procedures at a very high level, and to keep going, to keep training people, to keep reminding them, keep sharing incidents. Rob, anything else?
Yeah, I'd add to that what you say about we having the same incidents. That's possibly to misquote Trevor Kletz, the sort of father of process safety. He said, "Yeah, we don't have any new incidents. We just have the same incidents again." So it's that learning, and one of the issues is that corporate memory. So as Roger said, a company that has an accident, it will be, everyone will know about it, and it'll be investigated, and it'll be high profile within that organization or that sector of industry for a while. And we say these events keep happening, but still major process safety events are thankfully sort of fairly infrequent. And so people can go through their entire careers in high hazard industry and never see an incident. of the sort of thing that we're talking about. So it's important to keep sharing that, to keep it in people's minds. And one thing that BakerRisk do now is offer hazard awareness courses at our test sites in the US, where people can, and the response from industry to these has been amazing, because it gives people the opportunity to lose their eyebrows to a jet fire almost, or to experience the pressure wave from a vapor cloud explosion, and it gives this sort of first-hand reality of what these events are capable of, rather than just reading it in an accident report from 20 years ago, or seeing a video on YouTube. And so that helps people understand what they may have to deal with, rather than just reading a description on paper. So I think that's really important, that people have an appreciation and are constantly reminded that these things can go wrong. It's that sense of chronic unease, that what can go wrong today, what are we not doing, what can we do better.
Excellent. No, appreciate that. And to everyone, again, as I stated earlier, I know we've only covered a few of the questions that were asked and have answered a few, and just know that we are going to have our presenters, Rob, Roger, and Roy in the background, who's also been helping answer questions. They'll address the rest of them, and then we will send out and post their responses via email, newsletter. We'll post it on LinkedIn and also to our BakerRisk website, which will also have access to the recorded webinar, slides from the presentation, and again, the Q&A from today. Thank you so much, Rob, Roger, Amr, and Roy. Appreciate y'all's time and efforts. And this is a really just interesting subject. And as you can see from the questions that have come in, we may have to do another to follow up. So just appreciate y'all's time today.
Thank you.
Okay.
Yeah.
Thank you all very much.
Thank you. Bye.
All the
Stay
best.
safe. Bye now.
Yes.
Bye.
Bye-bye, everyone.